Good day everyone, our topic is all about apply Bernoulli's principle and continuity equation whenever appropriate to infer relations involving pressure, elevation, speed, and flux. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand the flow of fluids in the world around us. It essentially describes the relationship between the pressure, elevation, and velocity of a flowing fluid. It has countless applications. We can use it to explain of how planes generate lift or to calculate how fast liquid will drain from a container, for example. We'll explore this application and a few more later on, but let's start by reviewing the equation itself. Bernoulli's principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure or a decrease in a fluid potential energy. The principle is named after Daniel Bernoulli's, a Swiss mathematician who published it in 1738 in his book Hydrodynamics. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, P, which is just the pressure of the fluid. Then, we have the dynamic pressure, which is the function of fluid density, rho, and velocity V, and represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is the gravitational acceleration, and H is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of the equation, but it can be also presented in the head form and energy form. We can think of Bernoulli's equation as a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is really valuable information that can help us analyze a whole range of fluid flow problems. The equation does have limitation, which I'll over later on the video. But for now, the important thing to know that it can be only applied along a streamline. We can define streamline and steady flow as the path traced by a single particle within the fluid, or more technically, of a curve that all points is a tangent to the particle velocity. Let's look at the example where we apply Bernoulli's equation to flow through pipe, which is the charge in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with point 1 and 2 both on the same streamline. There's no significant change in elevation between point 1 and point 2, so the potential energy terms cancel each other out. And if we put all of the static terms on one side, we get this equation. For the change of pressure, if we assume that the fluid is incompressible, the mass flow rate at point 1 and point 2 must be equal. This gives us what we call the continuity equation, which is just the statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equal for the velocity at point 2. The cross-sectional area A2 is smaller than A1, which means that the velocity of the flow rate increases as it passes into the smaller diameter pipe. This is quite intuitive, as by substituting this equation for V2 into Bernoulli's equation, we can see that the velocity increases between point 1 and point 2. The pressure between both points must be decreased. This concept for horizontal flow is increased velocity must be accompanied by decrease in pressure is one way of formulating what we call Bernoulli's principle. It can seem counterintuitive because most people often expect an increase in velocity to increase a corresponding increase in pressure. But it makes sense if we think about the conservation energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy. Bernoulli's principle shows up a lot of different places. So, let's look at the example. Water flows through a horizontal pipe with a cross-sectional area of 4 meters squared at a speed of 5 meters per second with a pressure of 300,000 pascals at point A. At point B, the cross-sectional area is 2 meters squared. What is the speed of water at point B? Calculate the pressure at point B. So, if the cross-sectional area decreases, what's going to happen to the speed of fluid? So, anytime it decreases the cross-sectional area, the speed of the fluid increases. And the equation that we could use to get that answer is the continuity equation for an incompressible fluid. So, our formula is A1 V1 is equals to A2 V2. So, our A1 is 4, V1 is 5, is equals to our A2 is 2, V2 is equals to V2. So 4 times 5 is equals to 20. 20 is equals to 2. So 20 divided by 2 is equals to 10. Let's move on part B. Calculate the pressure. So the pressure at point A is 300,000 pascals. We need to calculate the pressure at point B. So will the pressure be higher or lower? One aspect of Bernoulli's principle is that the pressure is high when the speed is low, and the pressure is low when the speed is high. Because the fluid is moving faster at point B, the pressure has to be lower. In fact, as the fluid moves from A to B, it's accelerated. So therefore, there has to be a net force that will accelerate the fluid from A to B, and pressure is associated with force. So pressure is force over area. So therefore, in order to accelerate a fluid towards the right, the force has to be larger than the force at point B. So therefore, in order to get that net force in positive x direction, at point A has to be a high pressure and point B at low pressure. So now, let's calculate the pressure too at point B. So now, let's calculate the pressure too at point B. So let's use the Bernoulli's equation or formula. So P1 plus rho H1 plus 1/2 rho V1 squared is equals to P2 plus rho 2 plus 1/2 PV2 squared. So our P1 is 300,000 pascals plus 1/2, our P is 1,000, our V is 5 at point A, 5 squared, is equals to P2 plus 1/2 times 1,000, our V2 at point B is 10 squared. So 1,000 times 5 squared is equals to 12,500. At the right side, 1,000 times 10 squared is equals to 50,000. So 300,000 plus 12,500 is equals to 312,500 is equals to 50,000. So our 50,000 here, we can transpose it to the other side, so it becomes to negative. So 312,500 minus 50,000. So our P2 is equals to 262,500 pascals. So our pressure at point B is 262,500 pascals. So notice that it's less than pressure on the left side, which is 300,000. So as you can see, as the speed increases from 5 to 10, the pressure decreases from 300,000 to 262,500 pascals. As the speed increases, the pressure decreases. So now, let's work on this problem. Water flows through a circular pipe with a constant radius of 10 cm. The speed and pressure of point A is 4 meter per second and 250,000 pascal respectively. What is the speed of fluid at point B? What is the pressure at point B, which is 10 meter higher than point A? So you know that if the area decreases, the speed will increase. And if the area increases, the speed will decrease. However, the radius of the pipe doesn't change, so the area is constant, which means the speed has to be constant, based on this equation. So A1 V1 is equals to V2 and A2. So the speed is not changing, so the speed at point B is 4 meter per second. The only thing that changing is the height. Know the relationship between the speed and pressure, as we saw on the last example. If the speed increases, the pressure will going to decrease. So in this problem, the pressure is not going to change due to the speed. The speed is constant, so if the pressure changes, it has to be due to the height. So let's say point A is at a ground level. That means point B is at the height of 10 meters. So if we increase the height, what's gonna happen to the pressure? Now, in this first scenario, in the last problem, the pressure decreases because energy was needed to speed up the fluid from a low speed to the high speed. In this example, the pressure has to be decreased in order to increase the gravitational energy of the fluid in order to lift the fluid from point A to B toward. At low elevation, the pressure is high at the bottom and it's low at the top, so whenever you increase the height, the pressure decreases. So now, let's calculate the pressure 2 at point B using Bernoulli's equation. So P1 plus rho H1 plus 1/2 PV1 squared is equals to P2 plus rho H2 plus 1/2 PV2 squared. So our P1 or pressure 1 at point A is 250,000 is equals to 1,000 times 9.8 times 10. So 1,000 times 9.8 times 10 is equals to 98,000. So this 98,000 here, we can transpose it into the other side. So the 98,000 is going to be a negative. So 250,000 minus 98,000 is equals to 152,000 pascals. So our pressure 2 at point B is equals to 152,000 pascals. So if you really understand the lesson, you can try this problem. Calculate the pressure and speed of water at point B and C shown below.